Thank you very much. Thank you for the invitation to be here. It's really an honor for me to be here to talk about what we have learned in recent years about how the galaxy formed, thanks to the amazing data that has been collected by the Gaia mission, which you see, the European Space Agency mission Gaia, which you see depicted here on the top left. So the Milky Way is a conglomerate of stars, dust, gas, and dark matter that are held together by gravity. In the center of the Milky Way, we have the supermassive black hole that Rainer talked about. And what we have around the Milky Way are small galaxies, small satellite galaxies that orbit around it, the Magellanic Cloud. The whitish band that you see also on the sky and you see in this image is made of billions of stars that are too far away to be able to resolve them with the naked eye. But if you have a space mission like Gaia, then you can actually see these individual stars and measure the properties. What you also see in this image is these very dark patches on the sky, which are clouds of dust and gas, where new stars are being born, and with those new stars, also planets. The Milky Way is simply a galaxy, and in fact, it's a rather typical galaxy. It's a disk, and we're sitting in that disk, and so that's why we see that band on the sky. And about 2/3 of all galaxies in the universe, or the large galaxies, are disks. So it's a rather average galaxy, also in terms of how big it is, how bright it is. And because it's so average, it can be used to actually understand how galaxies in general form, what the physical processes are that play a role in the formation of galaxies, or in general, the physical processes in the universe, and also what the universe is made of. So for example, the question of what is dark matter. But the reason I'm mostly interested in the Milky Way is actually that I see it as our home in the universe. And we're all interested in understanding our origin. And so that's why we would like to know what the history of our galaxy is. And we have a fairly good model of how we think structure in the universe has formed and developed throughout time. And this is shown in this computer simulation that models the formation of a galaxy. So initially what you have is very tiny fluctuations that grow in mass because of gravity. In these density fluctuations, galaxies are formed. And so the first galaxies in the universe should have been small, and they are pulled together if they are sufficiently close by gravity to build up larger and larger galaxies, as you can see here. So that eventually you have a system that may look like the Milky Way. So this is a computer simulation, a very sophisticated one, but the natural question is this also how the Milky Way formed? How do we actually test that? So the nice thing about the Milky Way is we have, of course, a lot of access to an amazing amount of data, of very high quality data. We can see our galaxy in a lot of detail and measure the properties of individual stars. And what's nice is that stars remember where they come from. They have memory of their origin. So if you remember in that movie, what we saw is all of these mergers, so galaxies coming together and merging to produce larger ones. So if we zoom in on that process, so what we have is, here is a small galaxy orbiting a bigger one, say the Milky Way, and what we're seeing is how this tiny galaxy is being pulled apart because of gravity, because of tidal effect, and how it's merging, how it's contributing stars to the bigger galaxy. And at some point, you see these red stars are smoothly distributed in space. They follow the original orbit of their progenitor. But if you look at any given position, what you see is that actually the stars move together through space in streams. And so this tells us, if we find streams, this actually is telling us where the stars are coming from. In fact, there are some quantities that are conserved. There are some conservation laws that we can use, such as the conservation of energy or angular momentum. And because initially the stars were so clumped, they would also be clumped if these quantities are conserved. at the end of the day. So the clumpiness does remain, and that helps us find these different stars. But the other thing is that stars in their atmospheres retain an imprint of the environment in which they were born. So the chemical composition, the chemical elements, and the ratios of the different elements that we can measure in the atmospheres of stars actually reflect in which environment they were born. It's some kind of DNA, if you wish. And so if you find stars with different DNA, then you can tell they were born elsewhere. So stars are really like fossils, and so we can use them to do something like what we call nowadays galactic archaeology. But what we really needed to be able to do this is the Gaia space mission. And Gaia was launched in 2013, and it has been observing the sky, all the stars down to some brightness. It's been measuring very accurately as it spins the positions of the stars, and from the motions of the stars, one can infer how far they are from us, so their location in space. One can measure how fast they move on the sky. And also we have spectra, so using the Doppler shift, we can tell how fast they move away and towards us. We also measure the brightness in different wavebands, and that tells us about the properties of those stars, such as, for example, their temperature, but also their chemistry. And we've now measured this information for about 2 billion stars. So this is an amazing data set that is actually changing completely the field. So if we go back to the question of how did the Milky Way come to be the way it is, and we go back to this idea that, small galaxies were present first in the universe, formed first, like we see here in these snapshots from a computer simulation, then through time, these merge together. And at the end of the day, what you see is that a galaxy like the Milky Way would have a halo, and this halo is made up of the stars, should be made up of the stars that were present in these building blocks. Whereas most of the stars in the disk of our galaxy were born in the disk itself. So the question is, if we look at the Milky Way halo, what do we actually find? So the Milky Way halo would be stars that are orbiting in this region. And the Gaia mission has measured the motions for many hundreds of thousands, millions of these stars in the halo. And what we actually found is that the stars in the disk move in a very orderly fashion on circular orbits in the clockwise direction. And it turns out that about half of the stars in the halo are moving in the opposite sense. They're moving counterclockwise. Not only that, but actually the stars that are moving in the opposite direction, they're also very different in terms of their chemistry. And their chemistry actually tells us that they were born elsewhere. So what we actually discovered, as you can see in this computer simulation, is that the Milky Way experienced a very big merger some 10 billion years ago when the sun hadn't even been born. And this merger between what was then sort of a disk galaxy and this other large object led to the formation not only of the halo of our galaxy, but also led to as you saw in the movie, a different configuration for the disk that was present at the time. So this was really a milestone in galactic history. And after that, nothing much has happened. So this was really the last big merger. This is not the only object that one has identified in the Gaia data, but I was talking about, memory is still present in some conserved quantities in these invariants. And so what we expect is that in a space of energy and angular momentum, we should find lots of clumps that are associated to merger debris. And so if you run a clustering algorithm, for example, you indeed find lots of clumps. And what you should realize is basically all of these substructures are made up of stars that were formed in objects a long time ago, but these stars are really in our own backyard. So by studying these objects, actually we're learning about how the universe looked like at very early times. So we're really doing true archaeology by reconstructing the history in this way. What we would like to do is to construct something like a family tree. So if we have the Milky Way at the present day, we would like to know how its progenitors look like, its ancestors. We would like to characterize them. We would like to know when they merged, such that we have a full overview of the history of our galaxy. Of course, this work would not have been possible without the contributions of so many PhD students and postdocs that went through Groningen, but also the contributions of the Data Processing and Analysis Consortium of the Gaia mission, which consists of 500 astronomers and engineers spread out through Europe, all of whom contributed to this amazing data set, such that it's not just the data reduction, it's calibration, it's checking the quality of the data, it's making sure that it's publicly available to everybody in the world in a way that's usable for everybody. So if you're actually interested in playing with the data, you can go ahead and play with it. It's available to everybody. Of course, if you have a data set that has 1 billion entries, then you need software that can analyze this data quickly, that can explore it, that allows you to discover, for example, this merger debris. And so in my group, we developed a tool that's called VEX. And this tool is useful for many different things because it allows you to explore visually 1 billion points in less than 1 second on your laptop. You can, if you download this software, you can also play these kinds of games and identify interesting features in the data. But it's also been used also for the restoration of one of the most famous Dutch paintings, The Night Watch from Rembrandt. And this is the postdoc that actually developed that amazing work, amazing package. Of course, astronomy and technology go hand in hand, as both Reinhard and Michael said. And in the case of the Milky Way, of these measurements of the stars and their motions of the sky, which have been so crucial for unraveling how the galaxy was put together, one should realize that the technology that is needed requires to be able to measure the diameter of a human hair at 1,000 kilometers. So you see, you're really pushing the edges of technology. The turnaround of being able to measure this for society might be on the long term. We have enough examples to see that when you're driven by curiosity, you're doing fundamental research that drives this creativity that eventually returns to society, not only in terms of knowledge, of fundamental knowledge, but also in terms of technology. So I hope the next time you go out, I'm not sure it's going to work out this evening, and you look up in the sky, maybe when you go back home, you realize that actually Gaia is actually helping us to understand how the night sky was put together. Having figured out when the last merger took place means that we do live in a galaxy that has this white band on the sky. If the merger had been more recent, we would live in a different galaxy. So it explains what we're seeing at the present day. And to come back to the point that Michael made at the end of the day, we should really protect the night sky. We are all, humanity is under the same one sky. So we should really do everything we can to preserve it, because the sky gives us perspective about where we are, who we are. It gives us inspiration. It gives us the curiosity that we so much need to be able to live as humans. Thank you very much for your attention.
Thanks very much, Amina, for making us realize that our sky could have actually been very different and that it has a whole history of its own. It's not static. Everything is evolving in the universe. Again, I invite some questions. Yeah, go ahead.
Well, thank you for the nice talk. And it seems to me that paying attention to your talk, that we kind of understand very well what's going on. But maybe there is some missing point or something that we do not understand at all. Can you just say briefly what we do not understand at all in the Milky Way formation?
Yes, so there are many open questions. So I've taken you back 10 billion years in the past. But what happened before, for example, we don't know. We would like to really reconstruct the full history of the formation of galaxies. We would really like to understand how the universe looked like at early times. We're just at the beginning of this characterization of the different galaxies or the remains of the different galaxies that are there. I think the other point that is extremely exciting is if you have the motions, you not only have history, but you also have ways of testing gravity, just like we heard in the previous talks. And in this case, we have ways of testing what dark matter is. And so eventually, or maybe, what we will find from the motions of the stars is that actually gravity on the scales, on these very large scales, perhaps needs to be modified. I mean, that is a possibility. It's not my favorite possibility, but it is an option. So there's lots of different things, and the Gaia data is just so amazing that there are many discoveries across many different fields, just because you have such a big survey that observes everything that is there on the sky in many different ways.
You will go to Marcelo.
A real question, very simple. What is the reason of the name, with this name of milk, or this class, maybe?
Yeah, so I think this goes back to mythology. So I guess what you see is a whitish band on the sky, right? So I guess white. So there is this myth. I don't actually remember the exact details, but one of the myths is that actually there's this goddess that I don't know. There's this goddess that was feeding and due to some painful experience actually left the milk on the sky. Say, there's many in different. I guess in different cultures you have different ways of, say, explaining through a myth what this is. And milky comes from this, and it's also in Greek, and it's also in from Latin. We see that it's the same use of the name.
The final question.
Yeah, Amina, thank you very much for the nice talk. I have a question, but first a comment on what you just said, replying to the first question. You said we cannot go back to earlier time, the 10 billion years ago. That's true for the galaxies maybe, but should not give the impression that we don't know anything about the universe at earlier epochs, because with accelerators we can go back to a millionth of a million of a second after the Big Bang. So we know it happened, the Higgs field that permeated the universe and gave mass. The question is, can you elaborate a bit more on what we learn about dark matter from the Gaia data?
Yes, thank you. Of course, there are many ways in which we can go back in time, also by looking at very distant galaxies with the James Webb Telescope. So it's all very complementary, and that's the nice thing. We can check, the discoveries that everybody makes. Yes, so in terms of dark matter, so one of the examples is if what we can measure, so what we measure is the motions of the stars, right? And so what we can try to infer is what is the mass distribution in the halo of our galaxy. We can also try to infer how much dark matter or what are the forces that stars experience, for example, near the sun. So we could determine what is the density in principle of dark matter. So what we measure is mass density near the sun, from how fast, say, stars are moving in the vertical direction from the disk. So the pull that they feel as they move upwards and downwards, the pull tells you how much mass there is, for example, near the sun. And that's important, for example, for detectors of dark matter. But what you can also do is on larger scales, if dark matter is cold, one of the predictions is that there should be lots of dark clumps in the halo of our galaxy. And these dark clumps don't emit any light, but you would see them because they exert perturbations on the streams that we can see and we can measure. And it turns out that the streams of stars are very sensitive probes because they are basically stars that all move together through space. So if you suddenly see that, they've experienced a bumpy road, then you have a window into understanding what those bumps are, and therefore what dark matter is.